Welcome to section 0.6, Multiplying Probabilities. I want to first start off by mentioning that today's stuff is a little bit different than yesterday's stuff, because yesterday's stuff was more OR statements, or as in OR, or statements. Then that meant we had to add probabilities. Now today is going to be more AND statements, which means we might have to multiply probabilities. Now we're going to start off with vocab words again. We're going to start off with independent events. Independent events are one event does not affect the outcome of the second event, such as flipping two coins. If you flipped one coin and it landed heads, it does not mean the next coin has to land tails. So flipping coins would be an example. You could also flip coins, then roll a dice. You could roll a dice, then flip a coin. How you find independent events is that you multiply probabilities. So you would multiply this probability times this probability. Next is dependent events. The first event does affect the probability of the second event. A lot of the times you will see the words without replacement. So drawing one card, not putting it back, putting it on the table, then going back to the deck and drawing a card. So you could say drawing cards. You could also be picking something out of a bag without replacement. But I'm going to just say drawing cards, and that is without replacement. How you do that is the probability of A, then it is times the probability of B given A. That's how we read that. The probability of A times the probability of B. The slash means given A. So let's try a couple of them. First, does the previous spin affect the spin that you are about to perform? So does the first spin affect the second spin? No, it does not. So what does that make it? It makes it independent events. Independent events. So suppose now we spin the spinner 3 times. What is the probability that it lands on A, then A again, and then A one more time? Well, how do we find the probability of independent events? Look back to your last slide. We find the probability of independent events by multiplying the probability just straight across the board. Well, how many A's do I have? I have 3 A's out of a total of 6. So I'm just going to multiply 3 6 times 3 6. And that's going to give me, simplified down, 1/8. Now, does it change if I look for the probability of A, then B, then C? No, it does not. So again, it is still an independent event. What is the probability of spinning and landing on A? It is 3 6. Then totally different is B. The first spin does not affect the second. So B is 2 out of 6. And then C has only 1 out of 6. You multiply them together to get 1/36. Next problem. Now you have a bag contains 12 red, 8 blue, 11 yellow, and 8 green marbles. If two marbles are drawn at random and not replaced, what is the probability that a red then a blue marble is drawn? Well, is this going to be independent or dependent? It is going to be dependent. Now, how do we set up this probability? So we're looking for the probability, which is represented by P, red, then blue. First, what is the probability of red? Well, how many red do we have? We have 12 red. Now, how many total do we have? Over here in the corner, I'm going to go 12 plus 8 plus 11 plus 8, which is 39. So we're going to put this 12 over the total. Remember, probability loves total. So it's 12 over 39 times, now how many blue do we have? We didn't draw blue in the first round, so we still have 8 blue. But here is where it changes a little bit. Sorry, that's supposed to be an 8. Here's where it changes a little bit. We drew one, did not put it back. So how many are now in the bag? There are only 38 still in the bag. We are multiplying them together, so we come up with 16 over 247 after all simplified. If you don't want it like that, you can put it in a decimal, which is 0.064, or you can also put it in percent, which is 6 point, that's not a very good point. Let me get rid of that for you. 0.64%. Make sure you throw that percent sign on there. Now let's try a different vocabulary word, conditional probability, which is event A occurring given that event B has already occurred. So you are going to be given different groups that already have happened, and you're going to want to separate the groups into something that you can find, and that will make more sense on the example. But again, you're going to give two separate groups, and you're going to have to manipulate those two groups to find what we're looking for. So the formula would be probability of A and B, and then we would divide out that A to find the probability of B. So let's try it. At a restaurant, 25% of customers order chili. If 4% of the customers order chili and a baked potato, find the probability that someone who orders chili also orders a baked potato. I'm going to go back up here quick. Underline 4% order chili and a baked potato. With two groups belonging to 1%, that tells me that it's going to be conditional probability. So let's go ahead and see what our probabilities are. I want to break apart the chili and the baked potato because it says where you're looking for who orders chili also orders a baked potato. So if they order chili and a baked potato, we know that they're going to order that baked potato. So I'm going to start off with 0.04 rather, and why is that? Because this is a percent. That percent to a decimal is 0.04. So here I'm going to put 0.04, and I'm going to divide that by the 25% of those customers who order chili, because these guys do get chili, but they also get a baked potato. So if we divide out the chili, we should be left with who gets, or the percent that gets the baked potato. So you punch that into your calculator, you get 0.16, which is also 16%. And one more problem, or one more vocab word first, is contingency table, or it's also known as a two-way frequency table. All it is frequency of data from an experiment with two variables. So let's take a look at an example. So now we're looking at a pharmaceutical company, which is a drug company, that conducted an experiment to see the effectiveness of a new drug, like on the flu. Test subjects were assigned to two groups, a treatment group, which received the actual miracle drug, or the control group, which received a placebo instead of the drug. All a placebo is a fancy word for a pill that does nothing. Maybe is it a mental thing? So now here is our table. Remember what we like to do with probability? We like to find totals before we do anything else. So let's find the total stuff. So how many people improved regardless if they took the treatment or the control? We have 2,800 people improved. How about does not improve? We have 1,200. How many people took the treatment? We have 2,000. And how many did not take the treatment? We also have 2,000. So now we are asked, what is the probability that a test subject's condition improved given they were in the treatment group? So let's take a look. Here's our table still. And now again for the question, what is the probability that a test subject's condition improved given they were in the treatment group? All right, given they were in the treatment group. That's special to us because this given tells us that it's going to go on the bottom because of the whole treatment group. We have a total of the treatment group, which is 2,000. So I'm going to bring it up here. So to find our probability, we're going to take the number of people that were treated and improved. So treated and improved, treated up to improved. So there it is. So we have 1,600 divided by how many people were treated was 2,000. So now you punch that into your calculator. You can get 4/5, which is completely fine. You would get 0.8 if you kept going, or for probability, I like percents for some reason, I don't know why. It's up to you what you like, but 80%, and that does it for multiplying probabilities. Have a great rest of your day.